All right, how's everybody doing? How many of you are already do like machine learning stuff? Oh, okay. That's good because today I'm going to be explaining like how machine learning works, and they told me I could not move around a lot, which is going to be very difficult because I'm like half Hispanic, which means I need to like move around. And so thank you for that back there. Today we're going to do some deep learning with TensorFlow, and it's going to get kind of dodgy if you don't like math, and that's okay because at the bottom you can see, and I have my phone right here. If you want to stop me and ask a question, you can stop me at any time. But if you're embarrassed because like you feel like you don't want to ask a question because you might feel embarrassed, I have a little like a link down there where you can put the question in the box and it will text it to me. But this happens in America, and so I don't know how long it will take before you ask your question and it actually hits this. And if it takes a long time, you can go to the Twilio booth and complain to them. Because that's how I'm doing it, right? So hopefully this all works. Like my computer, like I said, blue screen right before. I don't know what happened. I'm on the insider build of Windows, which I should not do, I realize. So the problem with AI, I feel like, if you were in the last talk, because I caught the end of it, there's a lot of like weird thoughts that people have about AI, right? Like it's totally going to destroy our Earth or kill us because we've done just terrible things with AI, right? And I want you to be the first one to say that I don't think that's true. But like when I did AI, it wasn't that cool. And now all of a sudden everyone's like, hey, you know, we should do AI, right? How many people like have heard about AI all over the place, and now like if there's a talk with AI and at the end there's like a little bit of blockchain, like literally everyone will go to that crap, right? So I'm here to actually take the air out of that balloon a little bit because I want you to see exactly what it's doing. Because I don't want these, like, and I like Stephen Hawking, rest his soul, wherever you are. But when he said the things he said about AI, I felt like, hey, you know, stay in your lane of things that you know, right? And you'll see, and that sounds super like crass of me because rest his soul, you know, wherever religion you are, if he's dead or deceased or whatever. But please be aware that these things are not smart. They have no intelligence. They have no feelings. I was on a panel once with someone that was disgusted with me because he was like, well, that's how people used to treat animals. I'm like, well, they're not animals. They're computers. They have no feelings. And the problem with us humans is you can draw a smiley face on a rock and all of a sudden we feel like it's happy. Right? These are rocks. And we're going to draw a fat smiley face on it today. Okay? So I want you to be aware of that. It doesn't mean that I don't believe this stuff is great, but I think it's not as much as people think. Now, who here is a programmer type? All of you. I'm just going to assume you're all programmers. This is how we think about programming, right? We make an algorithm. We give it some input and out comes some answers. And the way that we do algorithms, you know this, is we come up with a series of steps to solve a problem. But there are certain weird problems that we get where we're like, well, okay, for example, let's just say you had to recognize like a number that somebody wrote. What do? Like as a programmer, the first thing you do is you're like, well, okay, can you give me lots of examples of the numbers, right? And then you're going to put it into a format where you can look at the numbers inside of the number, right? Like it's numbers, like between 0 and 255 if you do a black and white image. And then we're like, okay, so ones are like sevens, right? Like we're all like our programmer lizard brains are literally right now trying to figure out how to write this code, right? So you write like a bunch of if statements, you change some numbers, and it works, and you go home and you feel like you need to take an extra shower, right? You've all written code like this, right? Where there's like extra if statements or there's like weird numbers, and you feel dirty. Like you've done the wrong thing, but it works, and you don't want to tell anyone because there's a secret shame now in somebody's repo that you put there, right? Because that's how we do things. As programmers, we think of steps to a problem, and we give it input, and then we hope to get the right answer. Now, machine learning is a little bit different, right? The difference with programming and machine learning, and there was supposed to be a slide before this, but I'll pretend that I didn't say all this stuff, okay? Machine learning changes things so that we switch answers and we put it at the beginning, right? So machine learning is, and you probably all know this, this is from Francois Chalet, who writes Keras. This is his drawing. I changed the words. But now machine learning is, you give it answers and input, and it figures out an algorithm for you. Okay, that's machine learning. And that's basically the crux of it. And you all have problems where you've looked at data to try to come up with a series of steps. So if you've done that, stop it, use machine learning. Okay, because that's a better approach. Because it's really easy to solve something when you have like 5 columns and, you know, like 50 rows. But then, like some of the problems I worked on when I was in college, 15,000 columns and a couple million rows. Like there's no amount of showers that will help me write that code, right? And that's important to recognize. Okay, so in machine learning parlance, this is data, and then out comes this thing called a model, which in general we call algorithms. And what happens is with machine learning, you have to tell it the kind of algorithm for it to write, and then it figures out like the if statements or the 0.5s and the 0.7s, okay? You shouldn't think of it any other way than this. It's not magical. They don't think. It turns out that when you put a lot of these systems together that do well, it starts to feel a little magical, and that's okay too, okay? We're going to use TensorFlow as what's in our box, but you can use anything. You can use Keras. You can use PyTorch, Caffe, Theano, whatever you want. They all do the same kinds of things, but they all have their own ways of doing things. I like TensorFlow, but I'm liking PyTorch more nowadays. And so I'll probably, if I ever do this talk again, it's probably going to be with PyTorch, just FYI. So now that we know how to write this, right, our new multi-stage process of using machine learning is we get data, out comes this model algorithm, we plug that algorithm back into the way we usually do code, and then an answer comes out. Now, if you're smart, you're going to give your users an opportunity to validate that answer. Was this right? Was this helpful? If they push no, ask them why, and then you feed that back in, and then you do it all over again, right? Because as your data changes, so must your algorithm. Just like that time you're changing numbers, tweaking things to make it work, same thing with this. Now, you've probably all heard this or seen it in some way, shape, or form, but hopefully this makes it a little bit more intuitive, yeah? Okay. All right, so this was supposed to be before this bit, so pretend I didn't say that yet. Artificial intelligence is like this big bubble. That's not a really good term to use in the technology space. So this big area, right? Inside of AI, you have other things. For example, when you are talking about AI, there's different kinds of AI. The ones that I'm talking about, machine learning, is a subset of that. For example, when you're building a program to beat someone at tic-tac-toe, that's still AI. But that kind of AI is like more like a glorified search, right? And if you remember your stuff from uni, you remember that when you wanted to find the optimal path, you used an AI algorithm called A*. Or for example, when you were trying to do adversarial type games, you do something called minimax with alpha beta pruning, right? That's still AI, but it's not the kind that people talk about today because the search space is fixed. And then inside you have deep learning, okay? So that's what that's all about. And now pretend I said all that other stuff from before. So we can do this in post, right? Okay, so we're going to actually solve that number problem. And the reason, if you're all machine learning people, for us, this is like the hello world of machine learning, right? This is our hello world. And like I said, it's going to get dodgy fast. So if you need me to stop, I will stop. I am supposed to go through all the way explaining convolutional neural networks and how they work internally, but I can stop before that so that we can understand the previous things. I'm okay with that. Remember, and if you're afraid, just use that texty thing. And like I said, it'll get to me within 3 to 10 minutes. Okay. So as programmers, we want this program, right? We want this function. This is the function we want. Like when we get a number, this is a 28 by 28 pixel image. We want to give it to the function and we want it to return the right number. That's basically what we want. In machine learning, it's the same thing, right? We just want this function, let's just call it h, where we give it some data and it outputs the right thing. Because again, it's making the algorithm for us. But now for us, there's a little bit of a disconnect because we're wondering, what do these things actually look like in machine learning? Right? What does the x look like and what does the h look like? Right? That's a little bit of a disconnect for us. So what I'm going to do is I'm going to simplify the problem a little bit. And then we're going to look at our intuition and how that builds. And then we're going to see how that actually goes into something a little bit more complicated. And then I'll show you how that works in TensorFlow. And these things will get more and more complicated till we get to actual deep learning, okay? But I'll probably be asking you, is this deep learning yet? And you'll tell me yes or no. And if you're wrong, it's okay. Not very many people will laugh at you because there's not very many people here, and it's okay. All right, so we're going to start with this problem instead of the digits. This problem, it's a simple problem. We have a picture that's only 9 pixels, and we want to decide whether it's darker at the top or darker at the bottom, okay? And you're free to use your programmer lizard brains at this point in time, right? But it will become increasingly hard. Now, here's the thing. Over here, do you like this? Yeah, I know. Over here, remember, in order for machine learning to work, we need to give it the input, which is these series of 9 numbers, and the answer, which is 1. 1 simply means that it's darker at the top. 0 means it's darker at the bottom. And you can see, in row 1, that corresponds to the upper left-hand corner, right? Row 2, you see how that one is actually darker at the bottom? And then row 3, so on and so forth. So we're going to give the computer these things, and it's going to write an algorithm for us in such a way that says, when you give it the 9-pixel image, it's going to say dark at the top, dark at the bottom, okay? But let's just use our programmer lizard brains for a second. How would you solve this problem? By the way, if you are like a pedant and you talk about images, I do realize that the higher the number between 0 and 255, the lighter it should be, but I flipped them so that the slides would look good. Just FYI for those, because people will totally get out of it. I can't watch this. The numbers are wrong. But now you know I did it on purpose, okay? All right? So I'm going to let your programmer lizard brains look at this problem and figure out a way, how would you write an algorithm to detect whether the 3 pixels at the top are darker than the 3, collectively, darker than the 3 pixels at the bottom. And before we all get into awkward silence is basically only awkward for you because I taught high school for a long time. So how would you do it? So sum the numbers. Okay, so if we add the top 3 and we add the bottom 3, whichever one's greater. Okay, so let's do that, but let's draw some complicated diagrams to make us feel smart. Okay? And we're gonna change it around just a tiny little bit, okay? So I'm gonna draw this complicated thingy, right? So the X's at the bottom are the numbers that are coming in, like the pixel values. The W's are magic numbers that we are going to assign it, such that we do the adding thing. And once we multiply W1 times X1, W2 times X2, all the way through W9, we're going to add them all up. Okay? So what numbers would you choose for the W's to do the sum thing trick that we just discussed? So 1, 1, 1, right? Because that means that we're just adding the first 3. 0, 0, 0, because we're canceling out those 3 because we don't care. Now, what would you put for the last 3? Negative ones, right? Pretty easy, because if you do that, it's like, okay, if the answer comes out negative, then we know it's darker at the bottom. If the answer comes out positive, then we know it's darker at the top, right? Super easy. Any questions? That was a trick question. Of course you have a question. What is the B? Right? Okay, so let me explain this a little bit because we have too many machine learning peoples in here. Should I just go faster? I'm getting some serious eye rolls. Now, here's the thing. What if you want to predict that the top is darker, even though it's less dark than the bottom? But as long as it's just a tiny bit less, we still want to guess top. What you do is you'll add a positive number because it will bias it to guess towards the top, right? But if you want to bias it towards guessing the bottom row, you add a negative number, right? And that will force this algorithm to bias towards the top or the bottom. In machine learning, this has a very technical term. It's called the bias, right? This is the bias. This here, I mean, it's another way of looking at it, right? The X's go with the W's, and then we do this and blah. For those of you that love maths, and I use the S because I'm not in America, and apparently you have more than we do because we only have math. It's true. Go there. This is called the dot product of two vectors, right? You might have also seen it like in a scalar way as y equals mx plus b, right? That's the equation of a line, effectively, right? So let's test it out. So again, we're putting ones and zeros at there. The top is indeed darker, so the sum is 236. We guessed top. For a negative one, again, we put those numbers in. Minus 234, we guess bottom, right? See that? That, my friends, is machine learning. This thing is called a model, and that's called a prediction. That's embarrassing, right? In fact, for those of you that are machine learning people, if I put some kind of sigmoid around that and have a really different cost function, this is called logistic regression. Right? It's basically, right? And this is something that actually works on a lot of things. Okay, so this is good, right? We figured out that if we find this magic W, which we decided is 1, 1, 1, 0, 0, 0, minus 1, minus 1, minus 1, that if we multiply it by any picture that comes in, and our bias happens to be 0 in this case, then that will, if it's positive, we guess top. If it's negative, we guess bottom. Super easy, right? Well, what about Seth, if we want to be clever and we want to guess which one of all three is darker? How do we do that? Well, we just use 3 of them, but we do it at the same time, right? In order to do that, we have to put it into this box of numbers that I've named after my favorite 90s movie called The Matrix, right? Now we have 3 W's that are stacked. We have the 9 numbers come in, right? And I'm kind of like a 3rd grader at heart. And so whenever I see this kind of thing, I think of the Cookie Monster. Go with me for a second. You take that vector x, you grab it, you pull it out, you turn it on its side, and then num, 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 3 times the dot product. Right? So pull it out, and then num, num, num. Right? And notice that the top row is basically adding the top 3 numbers and zeroing out the rest and putting it the 0th location. And now it's easy, right? Because it's basically like adding all the numbers, and then we just pick the max index, and that tells us which row is the darkest one, yeah? It's pretty easy. And for those of you that are looking at this, you're like, this seems, it's not that complicated. We're just putting them into other structures called a matrix W. It's no longer a vector. We're dot producting it with an X vector, and then it's coming out with an answer. Now, here's the trick question. Can we add a bias term to this, and what shape is it? Yeah, because there's going to be a bias for each row now, and so if we do plus B, the B is going to be a vector of 3, a column vector of 3 in this case. Okay? So this is easy, right? But remember, so by the way, this is a new thing. We give this thing, and then it will give us, we max index, and that gives us the right answer route, okay? But remember, the problem was actually this. That's a bigger problem, right? We're going to try to shoehorn this puppy into the thing we just figured out, okay? So these pixels, these are 28 by 28 pixel images. They kind of look like this. If you squint and look into the matrix, you will see what number it is. What's the number? Rhymes with hero, starts with Z. 0, yes, good. Yeah. But remember what we did is we actually flattened the numbers out, right? And we have to also give it the right answer, right? So far we haven't taken into account using the right answer, but I'll show you that you need that. And this is what the file looks like then when we do it, right? And let me explain what this is doing. So over here, the features are just the pixel numbers. This is, right? This is the input. This happens to be the output or the answer, right? This thing. Remember how we had to have a column or a row for each of the answers? How many different answers are there to this problem? Well, it's a number. So you either have 0, 1, or all the way through 9. So how many of those values are there? Rhymes with hen. 10, yeah, you already said that, sorry. I have a hearing problem. That's why I'm so loud, I think, right? And this is a way of representing the right answer in that particular representation. So, for example, this is 0, 1, 2, 3, 4, 5, 6. That's the number 7. That represents number 7. What about this one? That's the number 2, 1, 0, 4, 1. Do you see that? That's just another way of representing the answer because we're trying to shoehorn our thing into fitting into this representation that we're going to do. In fact, that's called a one-hot encoding of the answer space is another way of looking at it. Okay, so just like we had this thing before, now we're going to have another thing. Right? How many answers do we have again? Well, we have 10 of them, A0 through 9. Right? If we had a bias, how many bias numbers would there be? 10, right? Because we have 0 bias for each row. Then we have this x vector, which is 28 times 28 long, which is 0 through 783, which makes 784 different things. Now, what does the w look like? Remember, you take this guy, you take it out, and you go num, 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 num. But you got to do it 10 times, right? So if we take this thing and flip it over, we're going to have 784 columns. And we're going to num, num, num 10 times, right? And that's what that comes out to be, okay? So now, this is where we get to that part of the problem where this is where you pick your own W's and it kind of works and you got to go home and take a shower. But we can't do that anymore, right? We got to figure out how to get all of these W's and B's, okay? And remember, I'm saying W's and B's with the assumption that there is a B there. I ran out of room, basically. Kind of like the picture thing, you know, with the pixels. So there's a B there as well that we need to take into account. So how do we get all of these W's and B's? And this is where it's going to get a little dodgy. But we have to be okay with that because I want you to know how it works and why it works so that when people like Stephen Hawking say this is going to kill us, the only reason it's going to kill us is if we give it bad data. It's not going to like come to life. I don't know. Maybe it will. So no, I don't think so. So the trick here is to get these W's and B's, we want to find the best W's and B's in such a way that we minimize the amount of mistakes we make when we predict a number, okay? So this is where it gets a little dodgy. So I'm just going to put it up real fast, and I'm going to take it away. We need to make a function, right, that describes or measures how bad we are at this, okay? And we're going to use this one. Don't be afraid of it. Remember, h of x is what we predict, and y is the right answer. Remember, we haven't used the right answer quite yet, but h of x is that function we're making, and y is the right answer. So let's do a little thought exercise for a second, okay? The thought exercise goes as follows. If our prediction function guesses a 2, and the right answer is 2, what does this function equal? 0. Okay, so if we get it right, it's a 0 in that case. If our function guesses a 3 and the right answer is a 3, again, 0. But if they're not equal, it becomes non-zero. So we want to do the best we can to make this function equal 0 all the time. And whenever we do that, right, you're probably wondering, why did I choose this? Like, there was a talk earlier this morning where he went through some of the intuitions. Like, I'm just a math guy. The reason why I like this function is because you'll see in a second why I like it. Okay. So in order to find the lowest point of this thing, we've got to find a mathematical or methodical way of doing it. So I'm going to do another thought experiment. By the way, this is the H function, you remember? Big W transpose X plus B. W being that ginormous matrix that's 784 by 10, right? B is a vector by 10, right? And then Y is that vector that's 10 also. Remember, that's why we put it in that way. Okay, so let's do a little thought experiment here. Let's pretend this is our function that we want to make equal 0. Where does this function equal 0? Yeah, I made it super handy. At 0, right? But pretend you don't know and you're blind. Everyone play Super Mario Brothers, or am I dating myself? You know the old one? When you were on a hill, dude's like, no, man, I'm a millennial. What's wrong with you? You remember when you were on a hill on Mario Brothers and you wanted to go down fast? What would you do? You'd push the down button and he'd slide on his butt. Remember that? We got to find a down button. Because let's pretend, and this is where I usually walk around, miss. I'm going to walk around. So pretend you're right here. Can everyone hear me? I'm really loud. Pretend you're right here on the right side of the curve. Are you at the bottom? No. Which way do you need to go to the bottom? Okay. Yeah, you need to go that way, right? You need to go to the left. But when you're looking at this, pretend now you're blind. How do you know that that way's down? So now it's a blind Mario Brothers. So what I would do is I would like put my foot back and be like, oh, that's up. Then I'd put my foot down. Oh, that's down. I should go that way. Now, if I'm at the bottom and I put my foot, I'm like, that's up, and I put my foot back, oh, that's up too. I'm stopping, right? So there's got to be a way to measure like that little thing. So again, I'm going to put my foot back a little bit, a tiny little bit. I'll put my foot down another tiny bit. And then I'm going to divide them. And that will give me a number that tells me how down or up it is. We'll call it dy by dx. Just out of sheer, because I want to. And then we'll make these infinitely small. And that's all of calculus. Sorry. Integrals measure the volume underneath. Now you have all of calculus, basically. So the question then is, how can we use this knowledge to find the bottom? So we'll do, continue this thought exercise. Does anyone know the derivative of x squared? Yeah, it's 2x. Like, this is really dumb. But whenever I look at exponential numbers like that, and I want to take the derivative, I think of like something falling from the sky, right? That 2 always is going to fall to the front. It like loses its status, and then it's like it's lost its brother, right? So if you have x cubed, that literally becomes 3x squared when you take, it's dumb, right? Sine is cosine, cosine is minus sine, and you just memorize this stuff after a long time, right? So let's use this function to our advantage, okay? So if I'm at x equals 3, what is the value of this function? Well, x squared, 3 squared, rhymes with hein. Starts with 9, yeah. What's the derivative of this function at 3? Well, 2 times 3 is 6. Right? And that number tells us something. It tells us that the slope is going up. So we want to go the opposite way. So let's subtract the derivative from that value, okay? So we're at 3. We're going to subtract 2 times 6, or 2 times 3, which is 6. So if we go from 3 and we subtract 6, where does that put us? Well, 3, 2, 1, 0. Where does that put us? Negative 3, right? Because 3 minus 6 is minus 3. What's minus 3 squared? 9, right? What is the derivative at x equals minus 3? Oh, seriously. It's too much for it. Sorry. I will use the extra math very soon. Right? Negative 6, right? So if I'm at minus 3 and I subtract 6, where does that put me? By the way, there's no such thing as subtraction. There's only addition of negative numbers. That helped me a lot in 3rd grade. I'm not kidding. Right? So minus 3 plus a minus minus 6 is 6 minus 3, right? Which again puts us at, okay. What's the derivative at 3? Do you see the problem? If I keep doing this forever, I'm going to bounce between 3 and 3, minus 3, forever. In fact, if I start at other values, I could bounce out. That's a problem. So what we need to do is we need to subtract a fraction of the derivative value. So let's pretend we start with a random w, right, because that's what we're trying to find. We have our cost function now that I showed you, you know, this one right here. We have our cost function right here. And what we're going to do is we're going to take our initial w, and we're just going to put random numbers in there. And we're going to subtract off a fraction of the derivative of that function. Right? This is called gradient descent. And alpha is called the learning rate. So hopefully with what you learned in the first class this morning, and this helps the intuition a little bit more. So we have, this is how you get the right W. You have to do the same thing with the B. By the way, this is the derivative. Oh, here's the thing if you want to be pedantic, because some of you might be. You see how I did like a d by dw, right? Because I'm dividing. When you have derivatives in multiple directions like we do, they're called gradients. But you're just storing them in a vector. It's like a vector of derivatives. I sound like I work on Wall Street. By the way, the derivative of the cost function with respect to the w vector is this. So you start with the w0. You subtract off alpha times that thing times x. And you loop. And then you take a measurement of the cost function. And so as you're going, you want the cost function value to go down. If it's not going down, you have a problem. Stop it. But you also want your accuracy value to go up, okay? By the way, this is derivative with respect to the bias. And this, if you want to go, for those of you that want to see this calculated, I can show you afterwards. Very simple. Very simple. Okay, so far we have x, the incoming picture, y, the right answers. We have the model function, we have the loss cost function, and we have the optimization method. Okay, and we're only a half hour in. Okay, this is how this stuff works. Okay, so let's try it out. Let's talk about TensorFlow. So TensorFlow is an interesting framework. Because what it does is it lets you create like a graph of operations, and then it lets you define a way to optimize those things that are inside of it. So the first thing you have to do is you have to define a graph, and the second thing is you have to run a session where it optimizes the numbers inside of that graph. And with TensorFlow, there's like 3 kinds of things that you can put into it. The first is this thing called a placeholder. You can see that at the bottom, which is a promise to give TensorFlow some values. A variable in TensorFlow is something that it can optimize, and a constant is, well, a constant. Those are the 3 things. So in this case, notice that x happens to be a placeholder because we are promising to give it the x, and the w and the b's are variables that it can optimize. Now, we're doing w transpose x plus b. Now, if you go back to your computer science days, when you're building the AST for a computation, this is what this would look like, right? So this is how we build it. You're probably wondering, well, linear model, I don't know. Well, here, it's just a function that I made to separate things. That's what it looks like in TensorFlow. X is a placeholder that's of size none 784. None meaning like I don't know how many rows I'll give you. Just be aware that there's 784 columns. I'm giving it a name. Now, the Y value, again, is none, but it's one hot vector of 10. Right? And that's the thing that we're giving it. That's that ginormous file that I was showing you before. Now, the linear model, you can see basically is I'm making a variable for W, I'm making a variable for B, and then I'm adding the matrix multiplication of X and W. I swapped them because of the transpose plus B. So I basically showed you how to build W transpose X plus B. There's no mystery here for this, okay? Now, the other thing we need to build is we need to build a cost function. Remember that cost function is this thing? That's what it looks like. Remember, because I had defined this function h of x, I could just use it in TensorFlow like that because it's going to continue to build this graph for me. Do you see the reduced mean? H of x minus y power squared. So that's what you're building. You're basically in TensorFlow building up a graph. Now, for those of you that are more advanced, PyTorch lets you do this dynamically. And so, for example, when you're running this and you're defining the graph, you're not running it with numbers. It's just building this AST that then later it optimizes. With PyTorch, it has something called AutoGrad, which will store the gradients as it's going. So you can actually debug it, right? TensorFlow caught on a little bit to this, and they have something now called eager execution for those of you that are a little bit more advanced. Now, I'm not going to show you all the other graphy things that you're going to build, but there's other ones like accuracy. I'll show you that one. Optimization, like remember, we have to do the gradient descent stuff. And then debugging in summary, because we've got to find a way to measure if the cost function is going down and if the accuracy is going up. So let's do a little example here, and hopefully this will work. I think my mouse died. Having a really good day, everybody. Okay. So here is the stuff I showed you before. There's the linear model, right? And I can right click and let me go to peak definition. This is Visual Studio Code, by the way, and you can see that it's basically. Oops, I went too far. There it is. W transpose X plus B. So it returns that thing. So let me close it. And then we have the reduced mean. And then there's the optimizer. It's already built in. Is this big enough? Can everyone see in the back? Cool. And then right here we have this accuracy thing. And this might look a little weird to you. So let me explain what it is. Remember that h of x is returning a 1 of 10 vector, right? The right answer is a 1 of 10 vector. So we want to pick the highest one, right? So you can see the argmax of h of x. It's picking the max index. Now, if that max index matches with the max index of the right answer, we got it right. So we're going to take the average of all of the ones we got right. You see how it built that graph up? If you don't understand, I can explain it again in Spanish. We get a vector out. That's not the thing we're predicting. Remember how we had top, middle, bottom, and the highest number told us which one was the right one? Now we have 10 things. The max index will tell us the one that we need to guess. That's what h of x does. But we don't want to subtract these things because that doesn't make any sense. We want to know if we got it right. So we pick the max index, or argmax of h of x, argmax of y, and if those two things are equal, we got it right. If we didn't, we got it wrong, right? And that's what that represents. Okay? Now let's go to the actual training code. You can see this train model thing. I'm just going to scroll up and show you what that looks like. Now, 150 and 151 are just me basically getting all of those matrices, like the numbers, like the right answer, the Y1 hot, and also the actual X values of 0 to 783. All the rows of that, okay? Now, you're looking at lines 153 through 160. This is the TensorFlow way of creating summaries so that while it's running, you can say, remember this, so you can actually see charts of how these things are doing. Because debugging machine learning is different, right? And you can see I have this summary writer that's going to write out to the log. Now, with TensorFlow, you have to initialize all of the variables so that they have an actual value, and then you kick off a session and run things. Now, when you're optimizing these things, you see 2 for loops, right? Well, this is how it works. Because you don't know how big your data set is going to be, you can't give all of it to it at once. So you chop up your entire data set into little batches. That's what the second for loop is for. So for each of the batches, run this optimization. You can see that in session.run. We're going to run the optimizer, which is that gradient descent optimizer, which holds the strings to the entire AST, right? Just the way I think of like graph theory is I always think, okay, if I were to pull this node out and hang it up, what would happen, right? If you were to pull the optimizer out, right, that optimizer has h of x built into it. It has y built into it, right? And inside of h of x, it has the b hanging off of it and the w hanging. It's all in there, right? And now the cost function is a separate function that we're going to calculate. What is the cost as it goes? But remember, the cost function is also built into the optimizer, and so we're good. And then the merge summary operation is the thing that we're doing to do the summary. So we're in the session, we're running 3 things at once. And remember, we promised to give it 2 things, an x and a y, and you can see that feed dictionary there. That's passing in the x and the y for each of the batches. Now, when you've done each of the batches, you've run through the data set, and in one time, that's called an epoch. You can do this for as many epochs as you want. Yeah? That's what the outer for loop is for. And then you can see right here that I'm writing out the summary values, and then I'm printing stuff out, and then I'm saving the model out. Because there is an output. What is the output of this? W's and B's. Right? Okay, so let's run it and see how this works. Everyone following me so far? Because we're already past the dodgy parts. I think. So I don't know if this is going to, like, it takes a lot longer to run the first time. I don't know if it's going to do that here. Usually I warm it up, but my computer crashed. So this is the warm-up thing. Now, I have a GPU in my machine, so it makes it a little bit faster. Why would GPUs be a good idea for these kinds of algorithms? Because I'm matrix multiplying all over the place, which is basically what all computer games do. All right, okay, here we go. This is the part that kind of takes a, oh, it did a good job. Okay, so there it is. It's running through the batches. There's 600 batches, and I think there's 60,000 numbers. Like, this is MNIST, so it's 60,000 numbers. And it's running through. Is it doing okay? Like, it looks like the cost function is going down, and the accuracy is going up, maybe. How can we know, though, if it's doing the right thing? Okay, 33 seconds to run that. How do we know it did a good job? Well, thankfully, there is this thing called TensorBoard that will show you how these things are doing. Right? So when I was writing out those summary variables, it was writing it out to this thing called TF events in the log directory, and TensorBoard can read these things. Right? Let me squeeze this a little bit to smooth it. Is the accuracy going up? Yeah. Right, you can see it kind of going up. Is the cost function going down? Yes, so we're doing something right. But the accuracy is just not very good. Right? Okay, so that's that example. Any questions with that? So in the output folder, there's going to be 2 different things, right? There's the log stuff with the events, and then there's a bunch of things that come out. And I want to show you what those things are, okay? Because I feel like this is the part where, like, everyone starts to say, and then magic happens. It's not magic. It's W's and B's. Okay, so there's 2 graphs that I want to show you, okay? One is really scary, and the other is not. The scary one is the model.pb. When I save this model out, right, it saves everything, right? Remember, we're just interested in the W's and the B's, but when you're doing the optimization, it does a lot of its own internal things to do the gradient descent steps to save it, and it gets kind of hairy. Let me show you how hairy it gets for that. This is the graph. How do I zoom out? Okay, I'll just fat finger it. This is the graph. This is hideous. But this represents the entire computational tree for the entire optimization. We just want the W's and B's. So I actually save those out separately, but through a process called freezing. And now you can see that the W's and B's are in there. Hold on, remind me later there, buddy. So here is the X is coming in. It's kind of hard to see. Okay, so the X is coming in, right? And then it's going to get multiplied by this thing called a B. Sorry, my computer is not being helpful. Uh-oh. Does anyone have any batteries, just out of curiosity? I think I lost all of my... Oh, there we go. Hopefully this will work. Okay. Like my escape key isn't working. This is so scary. Uh-oh. Okay. Okay. Okay, good. Whew. That was pretty scary. So here is the B right there. And I know it's kind of small, but it's just this vector. And I'm going to zoom in again, and hopefully it doesn't screw me over. Do you see that? There's the W. And now I'm going to go back to the B that we're going to add at the end. There it is. So TensorFlow figured out the exact W's and the exact B's that it needed in order to solve the problem. And those W's and B's produced an output that was of strength 82% accuracy. Now, you're probably wondering, well, what accuracy, what are you talking about? So what happens is you separate your chunk of data into, like, we're going to use this to train, and then the other chunk of data, we're going to use this to test to see how good it is. Right? And you can actually see that when I'm running it, at the end, I evaluate the cost, right, based upon the test data. I don't think I printed out. I think I think I printed out here, right at the end. Okay. All right, any questions about, oh, I already showed you that. Any questions about that? So basically, like, this AI is just solving the WB problem. So this is another way of looking at this same problem, right? Right, we're taking all the X's, multiplying it by this big W and this out thing. Is this deep learning? What if we stack it? It's not. Right, and here's the thing, and you're right, this is always a tricky thing, because a linear combination of a linear combination is still a linear combination. You have to add a non-linearity on the interior. Right, and so we're going to, like, just like you said, it's not. We're going to add a little function so that when the X's come in, we're going to non-linearize it. Now, the general rule is it needs to be a differentiable function, but that's not actually true all the way, because the one that actually works, the rectified linear unit, is not differentiable, but that's okay because they fudged it. That's why math people and statisticians hate machine learning people. Like, it's like that Anchorman fight, you know, between all the anchors. You ever seen Anchorman, you know, and like El Canal Ocho people, they come and they try to fight each other? That's like the statisticians. Okay, I think I'm dating myself here. So the question is this deep learning? Now that we put the activation function back in. The answer is we don't know. Right? Because when does neural networks, which is what this is, become deep learning? It depends on the marketing guy. Basically. Like, the more money they want to make, the less interior nodes you need to have, and they can call it deep learning. Okay? All right, so a little something about this. How do you find the derivative of this kind of function? right? Because that's what we needed. Remember to press the down button on Mario to slide on the way down? This function is considerably more complex because now we have big W's, 3 of them, plus a function that's being executed over all of them. Well, there's this interesting rule in calculus called the chain rule, which tells you that the derivative of a function that contains another function is the derivative of the outer function times the derivative of the inner function. Right? So if we want to find the derivative of the out node, it's the derivative of that function times the derivative of the one before it. But in order to find out the derivative of that one, we need to find out that times the one before that, times the one before that, times before that. So when we push the data forward propagation, and then when we're trying to find the derivative, we go backwards. So back propagation. We're not really clever with names. You should have named it like Steve or something, or Jedi. You know what I'm saying? That feels more exciting. That's how back propagation works. Okay, to find the derivative. And so, like, again, I'm like 3 years old. I watched Knight Rider when I was a kid. Remember that car, KITT? It had this little light at the front that went, it was scanning. I always hear the Knight Rider sound when I'm back propagating and forward. I don't know why that is. So here's another way of looking at it, right? What we're going to do is we're going to take this 784 thing. We're going to multiply it by a matrix that's 784 by 512, because I'm picking 512 interior, which means that the vector that comes out is 512. It's like we're making a new picture in the intermediate nodes. Then we're going to run the ReLU function over it, do it again. Then we're going to run the ReLU function, do 512 by 10, and then softmax on the way out. Now, you're probably wondering, well, what does the softmax do? I could take the softmax out, and it's okay. We'd still pick the max index, and that would still work. The softmax makes it look like a probability, even though it's kind of not. But it makes it look like a probability, even though it's kind of not. Just be aware of that, right? It's just a function that forces it to sum to 1 when you're doing it. Now, you're probably wondering, this looks super hard to do in TensorFlow, Seth. Right? That's it. You're probably wondering where the B is, or the W. Well, because W transpose X plus B happens so often, they created an abstraction over it because we're really good at programming. And so inside of dense layers, you have the W and the B living inside of it. And so now all we need to do is pass the X in, look at the inputs to that layer, X, and we want 512 on the interior with a ReLU activation function. We'll do it again. H2 hidden layer 2 with the input of H1 from before with 512 on the interior, rectified linear unit on the activation function. And then we do another dense layer for the output. We want 10. I could have done none on the activation. It would have been exactly the same, but I wanted to make it look like a probability, and so the activation is a softmax. And then I named these things so that I can grab the nodes, because what happens is when I freeze the protobuf file, which is the output, I need to put it into a program. And when I do that, I need to be able to access the nodes that I want. And the nodes that I want are the X coming in and the prediction coming out. So that's why I do that. Okay, let's run that thing. If the computer doesn't crash. I'm just kidding. Sorry. Okay, so I'm going to change this to multi-layer perceptron better. And I am going to change the cost function, if you don't mind. I think I started it. Oops, that's not what I wanted to do. Okay, don't look at what I'm doing. You're going to know all of my secrets now, which is really upsetting me right now. So I'm going to go ahead and just type up the new cost function real quick. Hold on. Real quick, just type that up. And you're probably wondering, well, what is that? It's just a new kind of cost function. Think of it like this. Remember how I said like a 7 minus a, like, is the difference between 7 and 3 like 5 for reals when you're looking at number drawings? So this is more like a categorical error. Like when we pick, like, so the difference between picking a 7 and a 3 should be the same as if you chose between a 5 and a something else, right? Because they're pictures, they're categories, right? It's like, what is the difference between hot and cold? Of course, it's pi. but it's hard to measure it. But you see what I'm saying? You can't subtract these kinds of things, so that's a better way of doing it. And I'm going to use a different optimizer because it's a little bit smarter, okay? And I'll just type this up real quick and hit save. Now, you're probably wondering, what is this atom optimizer? It's basically all gradient descent, but remember that we had problems with gradient descent because it could like go wildly out of place. Atom optimizers measure the momentum of the change as it's going through the optimization space. Because remember, we're not in 2D space anymore. We're in 784 space. And so Mario, I don't know what shape his butt is in to slide around, but he's sliding around, right? And so we don't want him to slide around too crazily. And so Atom actually modifies the momentum a little bit. And then it does another thing that I'm forgetting because I forgot. Okay, so now we're going to run this one here. Did I save it? Yes. So let's go here, and I'm going to run this one. And this one is going to do the same thing, right? But it's going to use a multi-layer perceptron with a different cost function with a different optimizer. And it's going to take a little bit longer, but it's going to be a lot smarter. Do you see how it's smarter? Like we basically went from 82% on the end run to 95. Now, you need to take this with a grain of salt, because if your data is crap, then it's really good at being crappy. Right, here's an example that's kind of not funny. Let's just say you're at a police department and you want to start predicting where crime is. But in the United States, we unfortunately disproportionately target African Americans and minorities for policing. So if you give it that data, what is it going to tell the police to do? So be aware. Like, I am less worried about these things killing us and us killing ourselves because we're racist and douchey. Forgive my French. So 97% accuracy. Let's go to the actual model so you can see it. So let's go to, this is the second one. So we're going to reveal this one in Explorer. I'm going to open this up here, the digits one. And I know it's small, so I will try to zoom in here.
Is that the training accuracy or the test accuracy?
It's the test one. I'll show you real quick so that you can see that. And because I was confused for that for a second, but then when I went over here, you can see that for each run, I actually print out the test accuracy. Because when it's spinning through, it's showing you the cost function, and then it staples on the accuracy of the test data for each epoch. Good question. Okay. So, just like you were thinking, you are literally getting X going in. We're matrix multiplying by this matrix thingy over here, right, which is 784 by 512. We're adding the bias value, which is going to be 512. And then we're rectify linear, we're like adding it. It's literally exactly what I told you. And so this thing, you take this protobuf file and you put it in a program. Oh, wow, I'm out of time. Any questions about that? Okay. So the last one I was going to show you had to do with being more cleverer, and I'm going to go as fast as I can without hurting anybody. So the problem with what we've just done, right, is that we've taken this and we've strung out all the bits in one line. But it turns out that these pixels being next to each other means something as well. Right? So how do we do that? And we're going to do something with filtering and pooling, okay? So remember, here's our magic vector that we invented before. What I'm going to do is pretend this is the picture, is I'm going to take, hold on, there it is. I'm going to take this one and then do a matrix multiply with this one and add them all together Cookie Monster style, and I'm going to put it in this vector over here, in this spot right, where's my mouse? Can anyone, there it is, right over here. Then I'm going to do it again by moving over, moving over again, and then putting it, and then doing it one more time and doing it again. Now this is one way of doing it, but notice that it actually distorts the picture, and we don't want to do that. So you can actually add these things called padding. So we're going to pad this a little bit. And now when I do the 3x3 thing, I come up with something that's the same size. Now let me show you what this actually does in a real picture. By the way, I didn't show you this, but notice how much smarter this other one is. But the cost function is a little bit different because it's a different cost function. So I'm going to go here and load up a kernel, load up this notebook. And what this does is this takes a picture that I'm going to show you, and it's going to multiply it by that matrix and put a picture out for you to show you what it looks like. So here's the 1, 1, 1, 1, 0, 0, 0, minus 1, minus 1, minus 1. Right, same thing I had before. And I am just going to open like an important picture, you know, from my life, from the wedding, obviously. And then I'm going to multiply it by this number, and notice what it did. It found the edges with that thing, right? So let me do this again with another one, because obviously kids are important in our life. And notice that again, it found the edges. Let me add one that's a little bit more serious. Uh-oh. Right? That one you'll see does a lot of things. So notice that with that 3 by 3 matrix, 1, 1, 1, 0, 0, 0, we were able to make a simpler picture, right? So imagine if we could create a bunch of filters to create a bunch of simpler pictures, and then let the computer decide about that. But we want to make sure that as we go down in the network, like the numbers get smaller, so we need to make it smaller, and so that's what pooling does. Right, so I'm going to change this to like a pool size of 1. Notice it's like almost exactly the same thing, but then the higher the pool size number, like it kind of like brings out the goodness. And let me show you what pooling is. What pooling does is, what we're going to do is we're going to do like this 2 by 2 pooling right here. We'll take the max value out of here and put it there. We'll take the max value out of here and put it there. Max value out of here and do it there. Notice that instead of like going 1, 1, 1 over, we're moving 2 over. That's called the stride. Okay, and that's the pooling bit. And so finally we come up with this other neural network, right, where we're learning these filters, adding an activation function, putting the pooling thing in there, adding another activation function, multiplying by a dense later, making it smaller, going down to 10. Now the question is, well, how do you figure out the filters? Well, we let calculus do it for us. And that's what I'm going to do next in this final and most amazing of all demos. Oh, this computer's going to crash because I said that. Now I'm going to change this, leave the same activation function, and then when I train it, you're going to see at the bottom. Well, I notice that it creates these things for me as I go. I notice this takes a little bit longer because it's trying to be a lot smarter. Oh, and this looks like it's having memory issues because I'm using the same GPU to project to the screen that I am to. So it's going to have, by the way, do you see the accuracy? Listen. It's the moneymaker right there. You hear that crap? Any questions about this? While it's going, I'm going to finish my slides here and warm myself by the fire of my GPU here. This is what the graph looks like. These layers are so well known and understood that they build them into like an abstraction. Notice that I have to reshape it back into 28 by 28 because I flattened it. That's why I reshaped it. I'm using 32 filters. The kernel size is 5 by 5. The one I was showing you was like a 3 by 3 one. And the padding is the same, meaning I want the image that comes in to be the same size as the image that comes out. So I put the zeros around it, and then there's a ReLU. There's the pooling, another convolution, another pooling. I reshape to flat, dense it, and then I output the prediction. I could have put on this dense layer a softmax again, but I didn't because I don't care. So I'm running that right now. It should be about done. There he goes, 81 seconds with the final accuracy of 98 on the test data. Data I had never seen before. Now you're probably wondering, what does it look like when you actually put it into a program? Well, I went ahead and did that because I like to be helpful. This is what it looks like inside of a program, right? I dropped a digits protobuf file in there, and I'm using TensorFlow Sharp, right? There's the input node, there's the output node. That's why I named it that way. And now when I run it, I'm going to draw with my finger numbers that it may or may not recognize. Okay? And I'm actually going to set a breakpoint on this p-value so that you can see it actually doing the right thing. And I know I'm a little bit over, so 3. I don't know if it's going to recognize that number, if I'm being honest. Uh-oh. That's a problem. I'm not going to be able to show you that. I'm sorry. I'll fix it later. Okay, so that bit was literally taking the numbers inside of that bag, multiplying them all the way through, and then getting the max index. But like I said, my computer crashed, and it's magical. Okay, summary. Machine learning is about finding h of x, giving examples instead of steps. Deep learning is one way to do it. We need x, y. We talked about linear functions, multilayer perceptrons, convolutional neural networks, mean square. We all did all this stuff. Here's how you can learn more about all this goodness, if you want. There's the code for this, for the thing I wrote. Okay? And if you want to get a hold of me, please do let me know. I'm happy to help. Thank you so much for your time.